Why can a tiny chunk of uranium power an entire city? Why do some elements spit out radiation even when nothing touches them? And how can something dangerous like radioactivity also save lives in hospitals every single day? Welcome to nuclear physics, the world inside the nucleus itself. Take a glow in the dark sticker and leave it near a light for a minute. It glows afterward because it absorbed energy and slowly releases it. Now imagine something far stronger. An atom's nucleus releasing energy all by itself. No light needed, no push needed. That's radioactivity. Inside every atom, the nucleus holds protons, which repel each other, and neutrons, which stabilize things. Most nuclei are stable, but some are imbalanced, too many protons, too few neutrons, or both. When the balance is off, the nucleus tries to fix itself by spitting out particles or energy. That natural process is radioactivity. Sometimes the nucleus throws out an alpha particle. Sometimes it shoots a fast beta particle. Sometimes it releases high-energy gamma rays. But the goal is always the same: reach a more stable state. Now here's something important. Radioactive decay is predictable, even though each atom behaves randomly. If you have a million unstable atoms, you can predict how fast half of them will decay. That fixed time is called the half-life. Short half-life decays fast. Long half-life decays slowly. This is how scientists date rocks, fossils, even ancient paintings. But radioactivity is only half the story. Let's move into something even more powerful: nuclear reactions. When nuclei split apart, fission, huge energy is released. That's how nuclear power plants work. The splitting of heavy nuclei, like uranium, releases heat, which turns water into steam, which spins turbines to generate electricity. When nuclei combine, fusion, even more energy is released. Fusion is what powers the sun, hydrogen nuclei merging into helium with unimaginable force. If humans ever master controlled fusion, it could provide almost limitless clean energy. And nuclear physics doesn't stop at power. It's deeply woven into modern life. Medical imaging uses radioactive tracers to detect diseases. Cancer treatments use gamma rays to target tumors. Smoke detectors use tiny radioactive sources to sense particles. Security scanners detect concealed materials through nuclear signatures. Food irradiation kills bacteria without cooking the food. Nuclear science is not just about danger, it's about precision, energy, medicine, and safety. Here's the curiosity to leave you thinking. If splitting or fusing nuclei can release so much energy, what actually holds the nucleus together in the first place, strong enough to beat the repulsion between protons? That question leads straight into the strong nuclear force, one of the fundamental forces of nature.